able to simulate like square pyramids.
Right.
So for this one, you can give it whatever shape you want.
All right. It is 2:10, so let's get started. Okay. So today we're going to continue expanding on the last sort of topic that we were talking about from Monday. So let's suppose that we have a variable or a data set with our response variable, and then we have a whole bunch of other variables, right? And so you've got this data set, you've got columns of variables that you're interested in examining, and let's say you want to create kind of the best model sort of possible, whatever that means, right? And last time we were thinking about this procedure that was really focused on understanding the trade-off between increasing your model complexity, right? So I could include all 4 of these variables. I could include, all the way up to, let's say you've got 100 different variables. I can think about increasing the complexity by just throwing in all 100 variables, right? But then we ran into this issue where you might be overfitting your data. And so really what we're going to be talking about now is how to sort of balance that and get our best model possible, and strictly defining that as sort of minimizing your total error. Okay. So what we're going to talk about today is, one, how to measure whether the model is quote unquote good, and then 2, the procedure to test different models. And really what we're going to be talking about with number 2 is really thinking about model selection in this particular case. And so thinking about, if I do have a bunch of variables, how can I sort of strategically figure out which variables to consider in the model? Okay, so for number 1, yes.
Does this also apply to the interaction terms of those variables if we're considering that?
I will talk a little bit more about that, but remember from last time, essentially what number 2 is going to do is automate ways in which I can walk through these 100 different variables in a faster-ish way. And so as it pertains to interactions, we cannot automate all the possible interaction terms. Those really have to come from intuition, right? So if I can't brute force this, right, which is going to be approximately 2 to the 100 combinations of variables, there's no testing procedure or anything that's going to help me walk through all of these possible combinations. It's just too many, right? 2 to the 100, that's more combinations than there are, particles in the whole universe, right? And if you wanted to do a brute force of all of the interaction terms, right, that actually explodes this up to 2 to the 2 to the 100, some-ish, right? And so not possible. So interaction variables really will be coming from intuition, yeah. Or some kind of suspicion that they are contributing in some way. Okay. So going back to that final example from last time where we were testing the errors, but testing errors of a particular set of data, right? It is data that you had left out that you did not calibrate the model on, right? So this principle looks something like this. So I have training data, and I use this training data to calibrate my model. And so this is like I've got a data set and I run some kind of regression on it, and that regression is then calibrated in the sense that I can figure out values for my betas, right, for my coefficients. Then I have a separate set of data called testing data, and this is what I use to see whether or not my model is good. Oh, let me. So this is my test model. And I can then, instead of looking at the metrics of my model from the initial calibration, I am using the test model to do things like looking at my R squared, my standard errors, my residuals, mean squared error. That's the probably the most common thing to sort of look at here. And so why do we do this testing procedure conceptually? Yes.
To test if the model's good?
Yeah, but why not just test if the model is good with the original data?
Because that's what it's used to train.
Yeah, right. And so, like, yes, that is what's used to train the model. Can you expand just a little bit in terms of why that might be problematic?
If you overfit, say, a model,
Yes.
you can get.
Yeah, exactly, right? So this is what we're talking about, right? So we are talking about, let's say I have my test data or my training data in red and my test data in blue. If I were to do this, right, that is essentially leading to an overfit of data. And so if I check all of my stuff here, my R squared, my mean squared error, it's going to say, oh, you've got the perfect model. But in reality, you've missed all of those blue points. And so really, we want to be able to measure my model against the blue points. And what you'll see is that maybe this red line would do a lot worse than if I just put a line through all of these, right? And in fact, I can even use information here about how well I'm doing in terms of like the mean squared error. And you can go back and recalibrate the model in some ways. And we'll figure out how to do that a little bit later on. Right, and so this is really informing us on how our model will hold up when you're predicting, right? So here, how does the red line hold up when I'm predicting against new data compared to a different model fit? Okay, any questions? So I'm gonna actually, let's see, we'll talk right now about a specific procedure that does exactly this, that is probably one of the more common approaches to doing this training testing data. And so this is known as cross validation. This is where we use data to artificially make a test set. So one of the struggles with using training and testing data is that the more data that I put into my model, essentially the better I can do in calibrating it. So you rarely will have an instance where you have this like convenient test set, right? Because if you did, you would say, well, I would like to make my model better and calibrate against that data, right? And so we have to think of ways in which you can strategically use your data and use as much data as possible, but still leave some data that you can test on. Yeah, unless you're in some kind of like coding competition, right? Netflix used to hold these things where they would give you a data set, and then whoever came up with the best model based off of like other data that they held back, you could win these competitions. But again, you don't see too many situations where you have this like convenient test set that's kind of held to the side for you. So what we do instead is we take our full data and instead I'm going to actually split this up into a training set. And then here, right, we'll have something like this. This can be our test data. And essentially what we're doing here is we're taking a piece of our training set out and then calibrating your model on the rest of the data and then testing it on this. So what are some potential pitfalls with doing something like this? What might you be worried about? Yeah.
Like not encompassing the full range of the model.
Yeah, exactly. By leaving stuff out, maybe there are important data here, or maybe it's like a range that just happens to be important to the set of data that you're looking at, or right that this could be a set of particularly influential data that may be sort of lost here. And so you can actually do this procedure multiple times. And randomize the test data. So instead, what I can do is randomly select other pieces of data. And I can run my model multiple times, and each time I can have a mean squared error for my blue set, a mean squared error for my green set, a mean squared error for my red set of data, and at the end you can average them, right? And this way I can test a particular model and robustly kind of be able to train it essentially across all of the data, but in portions at a time, and then test it out. And then if it so happens that like this blue one just happened to have like really important influential data, right? Your mean squared error might be higher for this one, but then it would get captured later on when you're emitting other parts of the data set. And so then you could average out that error. So this procedure is known as a k-fold cross-validation. And essentially what that means is if k is equal to 5, for example, then I will split up my full data into 5 randomly apportioned pieces, and then I will do this procedure 5 times, right? If k is 2, you would just do 2 halves, so you could split it totally in half. You would train on one half, test on the other, and then flip it, test on the original training, and train on the other one, generate 2 mean squared errors, and so on and so forth. So this is a really powerful way of leveraging your entire data set in order to measure out of sample, or to calibrate out of sample. Yeah.
Is there a threshold as to how large your full data set should be to decide how many of those k chunks can you carve out?
No, not really. Generally, I just suggest people do like 5-fold. One of the ways, it is context dependent. Okay, let me reverse that question to you guys. What things might I look for to maybe help decide whether or not I have enough k-folds? Yes.
Similar mean squared errors?
Yeah, perfect, exactly. So let's say I did k-fold of 2, and my first mean squared error is like 1, and the second one is like 1,000,000. What is that telling you about the stability of your model as it relates to your training versus test set, right? It means that the sample of data that I happen to choose is really affecting my model. And so let's split it up more and more. And so as you increase your k-fold, in theory, hopefully your mean squared error should be somewhat getting closer. And so, yeah, that might be a sort of qualitative way to think about your choice of how many folds to use.
So do you do like a hidden trial where you try different k-fold variations and see at what point your mean square errors start giving you similar values? Let's say you try like a 5-fold set and then you go 6, 7.
Yeah, you could do that. You could do that many times and then graph it and see what happens to your average mean squared error as you have more folds. Yeah, that is certainly a thing that you can do. Okay. So again, this particular procedure we're going to do a lot, and so we want to make sure we have a good sort of grasp of this. Yeah.
When we do multiple iterations on different training sets,
Mm-hmm.
each will generate a different model. So our final model will be an average of all of those?
Okay, careful with the nomenclature. Well, okay, no, I guess technically that's right. In terms of the structure of your model, they should be the same as you go through different k-folds. But you're referring to like the coefficients, right, of your model. So those will differ a little bit. But the idea is more that keeps going to sleep. Sorry. Okay. So the idea is more something like this. Let's say I have x1, x2, x3, and I want to test whether or not y equals beta 1 x1 plus beta 2 x2. let's just say that I want to test this. So there's a model with x1 and x2 and a model with x1 and x3, and I want to figure out which of these two give me better predictions for my y's out of sample.
Is it alpha 2 next to x3?
Yeah. It doesn't matter. The idea behind what we're doing here is that this will have some kind of mean out of sample mean squared error. Let's say this is for model 1 and mean squared error out of sample for 2. Once you've made a decision that, let's say, these mean squared errors are smaller than these, and therefore this model does a better job at prediction, I have essentially decided, okay, this is the model to go with, and now I can go back and train on the full data when I want to talk about these values. Even though you're right that these coefficients may differ a little bit in each of the training ones. Does that make sense? Yeah. Okay. Let's go to RStudio and come up with a procedure to implement k-fold validation. So I'm going to walk through kind of manually a construction of a function that's going to do k-fold. And a lot of times this will be kind of automatic behind the box, or it's like a black box thing built into some functions where you just say do cross-validation. But I think that because we employ this so much, it's important to have a really good grasp of like exactly what's happening behind the scenes. So we're going to walk through coding it ourselves. So cross-validation example. Okay, so I'm going to call this k-fold CV1. And actually, we are going to reuse our wages example. So wages is going to be, hopefully, oh, I need to do data table. Great. So we have our wages data set. So I'm going to test two different models using the cross-validation procedure. So I'm building a function, and the function is going to require two pieces of information: the data set that I'm going to use, and then the k value, which is the number of folds. And let's see what is happening here. Oops. Okay, so sample is a random sampling function in R. It takes the thing that you want to sample over, and it does a sampling some number of times and decides whether or not you're going to sample with replacements. Okay, so who can tell me kind of what I'm doing in these first 2 lines? Walk through this. And let's hypothetically say that we're going to do a 5-fold validation. So you can think of number of folds is equal to 5. Yes?
For each row in the data set, we are assigning a number randomly between 1 to 5.
Exactly. So I'm doing 1 to 5. I'm drawing the numbers 1 to 5 out of a hat, and I'm doing it with replacement, so I put it back in. And I'm doing it a number of times equal to the rows of my data set. And then I'm creating a new column called index, which is just based off that random sampling. So I have a table, and now I've added a column, and that column will tell me just randomly, it's going to randomly assign every row a number between 1 and 5, including 1 and 5. Okay.
Question.
Yes.
So when you train your model 5 times and you with these different data sets,
Mm-hmm.
those data sets are by definition all different data.
Yes.
They're not randomized each time with a subset.
Exactly. So you will never have overlapping data in a k-fold.
And then you mentioned the k-fold 2 would be half. You always split it
Mm-hmm.
by the number. You don't ever take like 10% of the data as your.
If I wanted to do that, then I could do a k-fold of 10, right? And then it would be
Okay.
10%
just
would
do
get
it
left
10
out.
times.
Yeah, and you would do it 10 times. Yep. Okay. I'm going to create this variable called mse.all. This is like my storage bucket. I'm going to just throw in the mean squared error that gets calculated every time I run through a model. So right now it's just an empty bucket. And we're going to do this some number of times equal to the number of folds that we have. Okay. So now most of the rest of the stuff is going to happen inside of this for loop, right? It's basically saying on 1, we're going to do some procedure. On 2, we're going to do some procedure all the way up to 5. We'll do some procedure. So the first thing to do, who wants to help me out here? What do I need to do? If we think about those like boxes that I drew from my full data going to training and testing data. We need to define some training data, and we also need to define some testing data. So how would I do that? You can tell me in English, it doesn't have to be in code. Yeah.
Yeah, training data is all the data where the index is not equal to n,
Perfect.
and then the testing data is where it is equal to n.
Yep. That's exactly right. So I define training data. I'm going to take my full data set, which is input, and then I'm going to say, well, I'm going to look at my index column, and I'm going to say if it's not equal to the whatever number I'm on, then that will be my training data, right? So if it's 1, I'm going to take all of my data, each row which has a random number 1 through 5, and I'm going to take all the ones that are equal to 1, and I'm going to set those aside, and those will be my testing data, and then everything that's not equal to 1 is going to be my training data. And as I walk through my for loop, once n is equal to 2, it's going to leave out everything that's equal to 2 as my testing, and everything else will be training, and so on and so forth, right? So every time I walk through my loop, my training data changes and my testing data changes, and that's entirely based off of the random sampling that we did from before. Okay. And now all we have to do is do our regression model. So I'm going to test 2 models. We're going to do from last time, earnings regressed on height, sex, race, and education. And note that we are not running this regression on our full data set, we are only running it on the training data. And then I want to be able to predict new values, but I'm going to introduce new data here, and that new data is going to be our testing data. So calibrate the model to training data, then use the coefficients that you made and just predict new earnings using data that you had not calibrated on. And I can then use this to calculate my mean squared error. So mean squared error is the mean of the, actually, well, I was going to ask, but I already typed it out, so. The mean squared error is based off of the actual outcome variable earnings in my test set versus what I predict, right? So in that chart, in the graph that I drew before of the red dots and the blue dots, it is taking the actual location of the blue dots that I have left out minus where the fit line would be corresponding to each of those points. And then you square it and take the average, and that is your mean squared error. And I can do something like this. This is going outside here, my empty bucket that's holding the mean squared errors. It says take that bucket and put in the mean squared error that I'm calculating for this particular fold. And then fill it up again every time you walk through. So if it's 5, you'll end up with 5 values of your mean squared errors and MSE.all. Okay?
Question.
Yes.
Can you explain predict the function?
Yeah. So I wish I could realize that with this setup I can't actually draw on here. So let me do this. So the predict function basically does something like this. If I draw a line here, this will be y equals beta times x. Or beta 1 plus something like this. The idea is x, well, let's say let's just say that these values are 1, 2, 2.5, 3, and so on. What predict does is it tells you the corresponding value on the line to each of these x's. In other words,
Okay, it can apply the regression model
yeah.
taken from LM.
Yeah, exactly. So
Okay.
so the value is equal to whatever value that we put in here, and this y hat is that dot on the actual line, and so on and so forth, right? So then y hat equals beta 1 of 2 plus beta 0. That would be this guy over here.
Does this have to be a linear model?
Yeah, it doesn't have to be linear. It will basically tell you the point on the line that you fit against the data. And so importantly, we happen to calibrate the data against these red points, but you can also predict on totally other sets of data. So then the idea here is that we have a test set, and I am predicting the corresponding y points for the x values in the test set. So it would be those points. And then I can then calculate, right, my error for the blue points. So that's what's happening over here, is now I'm predicting the points, and then I use those predictions to calculate my mean squared error as the difference between where it is on the line and where they are in reality. Yeah.
So training data is taking those each testing chunks out for each index number that you've assigned. Let's say you choose 5 number of folds. It's taking those out one by one.
The test set takes them out of the full data set. And then whatever remains is the training data,
Yeah.
and then what got taken out was the testing data.
So the training data is the one where since it's unequal to n, so not equal to n, does that mean it's taking them out there?
So let's say, let's say k fold is equal to 5,
Yeah.
k is equal to 5.
And for every
So if
set
this is, let's say this is 1, then the testing data is everything equal to 1. So how much of the data is in the testing data? How much of the data is in the training data?
the testing data only has those values, all rows except the ones with the index assigned as 1. All rows except the ones.
The training data, yeah.
Yeah.
So how big is that? How big would that data set be?
Everything but those assigned as 1.
What fraction?
What fraction? Sorry. Yes. If it's 5.
Essentially 1/5 then.
So the testing data would be 20%, and the training data would be 80%, right? So the more folds you have, the smaller percentage of the testing data that you will be having, and the smaller your k-fold is, the larger the percentage of the data your testing data would comprise of. Okay, so at 2, it's 50-50. At 3, it's 33-67, and so on and so forth.
And in the predictions command, you're putting the 20% that you took out back in and making the model extend its predictions and its observations to the chunk that you took back
Correct.
out and put them out.
That's right. Exactly. Exactly. So
Does the sample guarantee that you're gonna get?
it won't be exactly
It's
80%, 20%, roughly.
random, right?
Yeah, it's random. It'll be close. The larger your data set is, the
Well,
closer
if
you'll
you
be
encompass
to.
all the data in different chunks, then it'll be roughly.
Correct. Yeah.
Yeah.
Yep. Okay. So we'll do return MSE all. So let's go ahead and run this. And if I k-fold CV1 using the wages data, and let's say 5-fold, you can see the mean squared errors here. Okay, so these are the mean squared errors. So just to kind of reiterate a little bit, right, mean squared errors are going to be particular to the context of your specific problem. This isn't like an R squared, right, which is just standardized between 0 and 1. So these values are all relative to the context of your specific data. And let's go ahead and copy and paste this particular example. And let's call this CV2, and I'm going to change the model where I'm going to do age instead of height. Okay. And so the idea is I've got these variables, and I want to see which one is better at predicting, you know, the model that includes height or the model that includes age. And if I run that model, so k-fold CV2, we can see it returns another set of mean squared errors. And in fact, if I do something like the mean of these guys, oh, what did I do? K-folds. Oh. Oops. I have too many. Now I have a sort of direct comparison in the strength of my two models, right? And I can say that on average, this one predicts better than this one. And you can do like tests of significance to do comparisons and that sort of thing, right? Yeah.
Could you build that mean calculation that you did in the end in the function
Yeah,
itself?
you could.
And that would give you that one value, the average across the 5 then.
Yeah. And then one of the things that we were mentioning earlier is about the variation that comes with sampling. You could always run this a couple times and see how much that value changes, right? And it's not changing that much. You know, I ran it like 10 times or so. And you can see that it's never better than this other one. So we can be, you know, in my spur of the moment weird statistical comparison where I'm hitting up enter a bunch of times, but we can generally tell, right, that the second model is predicting better than the first. Yeah.
I tried it with 2 folds and 5 folds separately and it doesn't change much. Would that then suggest that because it's not changing a lot between 2 and 5, you're okay with 2 folds and you don't have to necessarily go with 5? Because it's not going from, I don't know, something like 74 million or something to 80 or 90, it's sticking between 76 and 74.
Yeah, although you might want to check it a couple times just to make sure that that variation isn't too big. Yeah.
Across the random sampling.
Yeah. Yeah. Okay. So one of the nice things that you'll see about this is that this procedure to do k-fold validation isn't kind of unique to like a linear model. or unique to the way a particular data set is structured or set up, right? And so this procedure we're actually going to use for all sorts of models, all sorts of linear, nonlinear, non-parametric models. And this kind of procedure is, again, super common, especially in the world of model predictions, to basically determine how good a model is. And you can always do comparisons of these things as long as your explanatory variable is the same and you're kind of looking in the same data set, right? You're allowed to do these sort of direct comparisons. So we'll keep that in mind. This is a very powerful tool, and it is a very adaptable tool across all sorts of models. Okay, yes?
Do you generally do cross-validation like this when you're doing it, or do you use a function that does this?
Oh yeah. No, this is definitely common enough where you don't have to write up your own custom functions. Usually it's like, usually there will be options to say run a CV and then how many folds. It's built into tons and tons of functions that we'll see, and we'll see examples of that. But this is just a way of getting everyone to kind of understand what's going on behind the scenes when you do like a built-in CV function. Okay. Okay. Any questions about this before we move on? So I'd mentioned at the beginning of today's lecture that there's essentially two things that we are focused on today. One of them being that a procedure, or I guess, yeah, kind of the procedure that we can take to do this sort of validation. And now I'm going to talk about sort of related methods that are specific to a subset of measuring how good the model is, and that has to do with model selection. So, what is model selection? This is the task of selecting a statistical model from a set of candidate models. So, same thing that I was talking about right at the beginning. Suppose we have all of these variables. Which model is best? We've got all these combinations of models that we can do, right? We explained that there's like 2 to the n number of combinations for all of these things. So if we think about the procedure we just talked about with cross-validation, well, that's going to tell you which one of these is the best, but it's not going to really give you a strategic way of testing all of these, right? Because you could brute force through all the combinations, but you would rapidly reach these points where you're butting up against computational capabilities. So we're going to dive into strategic ways of doing this model selection. But before I get there, we're actually going to talk about a couple other criteria besides cross-validation that are actually commonly employed as sort of shortcuts. Because these other criteria are, let's say, a little bit easier or more straightforward to implement. They are essentially proxies for doing cross-validation. They represent sort of similar ideas in principle to what the cross-validation is doing. And so cross-validation, you are doing this kind of simulation process of like going through all of your data. And sometimes that can be complicated enough in a way where you might prefer doing something a little bit simpler. Okay? So, criteria for model selection. So these are kind of some of the more common ones. So one, I never know how to pronounce this. Akaike information criteria. I don't know if someone actually knows how to pronounce that.
I think it might be accurate. That's how David Burns says it.
Sure, we'll go with that.
Yeah.
Akaike. Okay. So this is also known as the AIC, which is how I will be referring to it. So this is an estimator of the relative quality of the model, and smaller is better. So AIC is equal to 2k minus 2 ln of this. So k is the number of parameters, and L hat is the maximum likelihood. So smaller is better, okay? So my likelihood is essentially a measure of how, let's say, how right the model is, okay? So let's say, generically speaking, the better the model is at predicting the outcomes, let's say that this value is higher. So you have a negative associated with the likelihood value, and so this term will make my AIC smaller, right? But if I have more parameters, my AIC value goes up in value, okay? So this structure is related to our concept, right, of model complexity and total error. You're probably going to do a better job at predicting outcomes, at increasing your maximum likelihood value as you put in more parameters, but my AIC will be penalizing you. So it is in essence trying to say go this direction with your maximum likelihood value, but go this direction with your number of parameters. So the AIC is exactly built on this concept that we've been talking about. And just for reference, in a linear model, the AIC ends up looking something like this. 1 over n times sigma hat squared RSS plus 2k, something like this. Okay, so that's the first criterion. There's another one. This is known as Mallow's CP. So reduce the RSS while taking into account the number of parameters. And in fact, this is equivalent to AIC for linear regressions, or at least it's proportional. So the equation for this, 1 over n, where this is your sample size, RSS plus 2k so this is our residual sum of squares number of parameters. And this is our estimate of variance. And so this is exactly the same as the AIC in the linear model. So let's walk through this one again. Let's say, quote unquote, the better my model is, or the better that it is at predicting, what happens to my residual sum of squares?
Goes down.
It goes down, exactly. And that's what we want. So the better the model is, the smaller the RSS, the smaller my CP value is, my Mallow CP, and therefore the criterion is saying that it's a better model, but you have to balance against this, right, which is increasing your model complexity to improve your RSS is actually going to penalize you, right, because this term will get bigger as you add more variables into your model. Same thing, right, we're doing our trade-off between model complexity and number of parameters versus reducing the bias in the model. Okay? So both this and the last one we looked at are both operating under the same principle, analogous to what the cross-validation is as well, like balancing complexity versus predictability. Yeah.
The sigma hat squared, is that the estimator of variance of the error term? If so, why was it in the numerator in the AIC formula, and here it's, sorry, the denominator, and here it's in the numerator? And what happens if that's going up and down to CP and AIC?
Yeah, so it doesn't actually affect them differently. So in here, it was here and over here.
Yeah.
It just changes the proportion, the that they're that they're in sort of comparison to. And so the AIC won't exactly equal to the CP, but it will be proportional to the CP, and it will remain proportional as your model changes.
So is this the variance of the error term then?
Or
Or is it the some sort of variance of the estimators that you then use to compute?
So I want to say it's the variance of the estimators, although
But then wouldn't
how
there
would
be like
you?
multiple estimators?
Yeah, exactly. Yeah, I guess by logic then it should be the variance of the errors, although I'll check that.
I mean, even if it was
But they're all gonna be.
yeah, calculate using that only, so
Yeah. It's
so
it's
it
all
would
gonna
be so
uh,
that there should be the estimator variance of the error term then.
yeah, and this will vary a little bit as you change your model, but not to the extent where it's really going to be. It's unlikely that this term will be drowning out everything else, right?
But if in the AIC formula it was in the denominator.
It's in both the numerator and the denominator.
Oh, okay. Pretty sure the formula.
Yeah,
anyway.
let me jump back. Here. You can see it's both
yeah.
here and here.
Is it the same? Because I thought it was different. There was sigma hat squared and sigma squared in the AIC formula. Is there a hat missing in the AIC equation?
Oh, yes, probably. So there should be a hat. Oh my gosh. Here we go. Hat. Okay. So we'll look at just a couple more. Bayesian information criterion. So similar to AIC, but with different penalty for parameters. So in this case, it's BIC is equal to the natural log of n times k minus 2 times the natural log of your likelihood So you'll see that this form is pretty similar, but here, instead of, I believe it was 2 times k for your AIC, it's ln of your sample size times k. And so the penalty function for your parameters is pretty different. And it's actually dependent on the size of your data. So like the AIC, it's better if smaller, and this will have a bigger penalty on models with more variables. Okay. I'm going to talk a little bit more about the comparisons between all these in just a second, but let's go through our very last one, which I've been making you guys wait on this one for a while now, I feel like. Adjusted R squared. So this is equal to 1 minus RSS over TSS. So this part of it is exactly the same as before, but now we have an extra term here.
Is that the penalty for including?
Yeah, so let's think about it. So n is our sample size, and k are the number of parameters. So when k is getting bigger, you are increasing your model complexity. So help me walk through this. So as k gets bigger, how does that affect our adjusted R squared? Yeah.
The RSS by TSS would essentially get, I'm thinking, smaller.
It's like it's a negative on a denominator, right? So if this gets bigger, the denominator gets, what happens to smaller? When you divide by a smaller number, then this term gets bigger. So the more parameters you have, the larger this term is, and therefore you are subtracting a larger term from 1, and so
Your R squared
your
gets
R squared, your adjusted R squared goes down as I have more parameters, right? So what's happening here? This is essentially our regular R squared, but if I try to increase the model complexity by throwing more variables at it, it will be penalized, right? And so there's this trade-off behind trying to get this term as good as possible versus including more variables to do so.
And
So,
is-
yeah.
Is it not going to change if you increase the sample size then and keep the number of parameters the same?
Yeah, well, that's a different effect, but yes, adjusted R squared also thinks about how much data that I have. Yeah. But hopefully you guys are seeing the trend now, right? Our AIC, our MalloCP, our BIC, and our adjusted R squared are all introducing penalties into my ultimate criterion that's basically saying, yes, your model's going to do better when I include more variables, but I'm going to penalize you for doing that because I don't want to risk overfitting, essentially, right? So that same principle, it's all connected to that graph we were looking at about complexity versus our total error. These are all different measurements of trying to get to that trough in the total error. So let's talk a little bit about what the different types of criteria do for you. So adjusted R squared versus AIC, CP, BIC. So the R squared or adjusted R squared tells you how well does your model fit new data. Sorry. My eyes jumped to the next line. How well does your model explain observed data? Whereas AIC, CP, BIC tells you how well will your model fit new data. And in this case, this is higher equals better. And these are all lower equals better. But all of these will penalize more parameters, right? Then we have AIC slash CP versus BIC. BIC is argued to identify true model as n approaches infinity, and AIC minimizes selecting a bad model with small sample sizes. In other words, BIC is better when you have a lot of data, and AIC is better when you have smaller samples. And where is the cutoff? I don't know. It's kind of arbitrary. I mean, it's based off of the principle of the equation itself. AIC is a more conservative measure, whereas BIC scales with the size of your data, right? And what's the other method that I left off here besides AIC, MLCP, BIC, and adjusted R squared?
MSE, validation.
Yes, exactly. You can, that is the most direct way of measuring the prediction outcome, right? If you directly measure your test error with cross-validation, that is the most accurate measure of essentially how good your model can be. But because it can get computationally intensive sometimes, we use some of these measures instead. Yeah.
How is that likelihood calculated? Is it doing something similar to cross-validation, or is it, because if that's the term that's using both AIC and BIC and CP, then how is it calculating that?
Yeah, so there's some models. So when we think about like a linear regression, you are doing this minimization of your sum of squared errors type thing. We actually, in certain models, you use the likelihood instead because our ability to calculate a fit in the same way that we do in a linear regression might not be available. And so in a lot of cases, you're calculating the likelihood anyways, and therefore they're using that to then calculate your AIC and BIC because that like number is already available. And we'll talk about the actual calculation of a likelihood function a little bit later when we're looking at models that actually employ that instead of the OLS.
But in those models, isn't the likelihood of some explanatory variable changing the likelihood of your outcome variable in some way? And how does the AIC and BIC method imply, what is the likelihood of? Is it about your model being correct? Or
It is that. It's that exact value that you're talking about, right?
But then here, the outcome variable isn't the likelihood of something, it's the likelihood of, it's some value of the outcome variable, that's not the likelihood, is it? Because then we'll be talking more of a linear probability model, but here we're employing this for just linear regression.
No, actually, AIC BIC is not commonly used with linear regression. It is being used in the
linear
models where,
probability model.
yeah, exactly.
And so if you're doing a test on how to do linear regression models, should you stick to MSE?
Yeah.
Just R squared.
Adjusted R squared.
Okay.
It's pretty uncommon to use AIC BIC to in a linear model because then you'd have to go back and calculate the likelihood
Yeah.
probabilities, and that's like not something that you would traditionally do in a linear
Yeah,
model.
So this is much more useful when you're doing the probability models. And y is a probability between 0 and 1.
Yes.
Okay.
Yes, you'll commonly see AIC BIC being employed in like logistic regression and that sort of thing. Yep. Okay. Any other questions about these criterion? Okay, great. Oh, sorry, didn't see your hand. Yes.
Yeah, so can you go back to the
Yes,
example?
let me go back. This one.
Thank you. So a lot of times when you see the model results, when people report the AIC, sometimes the number is really large, sometimes the number really small.
Yeah.
And which would be different models.
Yeah.
Does that mean those two measures only meaningful when you choose a model among relative similar model targets instead of like so different model design?
Yes, exactly right. So AIC, CP, and BIC are employed to model as a direct relative comparison where you have the same same response variable or outcome variable. So if you have the same Y, you can employ a direct comparison. Adjusted R squared is going to be generally between 0 and 1 no matter what. And so this type of model, or using adjusted R squared, is more sort of universal to do a comparison.
That also means when you say it's usually when the number is smaller than the model performs better.
Yes.
But when you say like a single model that reports very large number, there's no meaning to judge the model at all, right?
No, that's right. Exactly. Yeah.
Yeah,
I do
always
find it
wondered
kind of
that.
funny sometimes where someone shows a regression results and then they show the AIC, BIC, and it's like, well, okay, cool. It doesn't really mean anything because you didn't compare it to anything, but yeah, that does happen. Yes.
How would the AICBA sort of be affected if, let's say, you're comparing, let's say, you have the same outcome variable, but you're making two different models with different explanatory variables?
Yeah, that is when you would use this. Yeah, that's when it is useful.
And the complexity for me comes in when sometimes I've noticed that if I'm adding more variables and there's missing data for some of them, the regression omits the explanatory variables, there's missing values and sort of changes the n value.
Yes.
And so would that then affect the calculation of AIC, BIC accordingly, because it's accounting for those missing data points, even though you're increasing the number of parameters?
That's only going to show up in your BIC.
Okay.
Yeah, because AIC and CP are not directly a function of your sample size, right? There's no n in those equations, I think.
Yeah, but for, I think it's mallow CP, it's relevant. The n is there. So
Oh yeah, no, okay, sorry. So that'll be true for CP and BIC, but
not AIC.
not AIC. Yeah.
So the AIC is in no way rewarding you or penalizing you for having a larger sample size?
Not directly, but it will in the sense that like your likelihood is probably getting affected.
Calculated by that n.
Yes.
Okay.
Yeah, so indirectly it will be. Okay. So now we have the tools to figure out relatively how good a model is. Now let's think about the procedure to actually figure out model selection. We're going to go through a couple of different approaches. Let's see, today we'll have time to go through kind of the more traditional approaches, or more traditional approach. And this is known as stepwise regression. So the more combinations of variables there are as k increases, right? The number of variables in our data set. And who's heard of stepwise regression before? A handful of people. This is a useful procedure and common procedure in sort of traditional regression approaches, but it's actually mistaught in a lot of classes sometimes. So you do have to be careful with the procedure that gets represented, the procedure that you use to execute a stepwise regression. Because to be honest, it is common for some reason to teach it in a very idiotic way. We'll put it that way. So I'm gonna walk us through how to do this, and then I'll talk about some of the common pitfalls of how people have taught this before. So forward, stepwise selection. Also found that I should mention that this is one of the more confusing algorithms. So if things are not clear to you or not straightforward, definitely let me know and I'll try and sort of clarify. So let's say we have an example where we have y, x1, x2, x3. Actually, let's just do these three. So let me walk through the procedure first, and then we'll do a manual example. So choose a model with no predictors. For k equals 0 up to total number of predictors, big K, we're going to do add one additional predictor, test all different remaining predictors, and B, select best as having smallest MSE or biggest R squared. Select best overall based on selection criteria. Okay. What the heck does that mean? So let's walk through this example kind of manually to see how this works. First, we are going to run the model like so. x1, beta 2, x2, beta 3, x3. And let's say the r squared here is equal to 0.8, r squared equals 0.9, and r squared equals 0.7. I will then pick the one, so this is step 1. So I will pick the model with the best r squared, and then I will use this to proceed to my next step. And in step 2, I'm going to test combinations, adding one variable at a time. Always starting with the variable that I've decided to keep into my regression in step 1. And let's say the r squared here is equal to 0.91, and the r squared here is equal to 0.94. Then I will pick this guy because it has the best r squared. And then we'll go on to step 3. I'm going to start with beta 2 x2 and beta 3 x3. And in this case, I've only got one variable left. So it'll be here. And that will be my final choice. And now what I will do is amongst all 3 of these, which has the highest adjusted r squared or AIC, CP, BIC. And then whichever one that is, let's say it's this guy, that will be the sort of answer of my forward stepwise regret selection procedure.
So the more x's you have, the more steps you'll have to do and compute.
Yes, but let us think about the computational complexity of this. How many regressions did I need to run for 3 variables? 6, okay? 1, 2, 3, 4, 5, 6. How many possible combinations of regressions could I run based off of the number of variables that I have? To the end, right? So approximately 8. So I'm actually saving some computational complexity. And in this case, you're like, well, it's only 2 more regressions. What's the big deal? Let's introduce one more variable. And let's count. Let's say I have x1 through x4. In step 1, instead of 3 regressions, I would have 4. So 4. In the next step, I would have how many? 3, so that's a total of 7. In the next step, I would have 2, so 9, and then the last one, I'd have 1, so I'd have 10. Okay. And how many actual combinations are there? 2 to the 4th, right? So that would be 16. So the number of combinations of regressions that I would run is k like that versus 2 to the k. This goes up very, very rapidly, right? So let's say I had 10 variables. That would be 10 plus 9 plus 8 plus 7 plus 6 plus 5 plus, right? What is that? It's like 50-ish, roughly. What's 2 to the 10th? It's a big number. Yeah, right? So this scales like linearly-ish. This scales like extremely exponentially. And so this procedure is exactly a shortcut to help us try and do model selection and walk through combinations in kind of a strategic way in so far as possible to look at the sort of world of combinations that I could look at, that I could have in my variables, but exclude some things that I think may not be necessary, right, to look at every possible combination. So what is a pitfall of this procedure?
I had a question.
Okay,
In
yeah.
all of these formulas, we're calculating how many combinations of regressions you have to run, or the number,
Yeah.
such as the interaction term one, and this one right here. Do all these exclude the beta nil, which is the intercept?
Oh, that's not, yeah. I mean, you can have a constant for all of these, right?
And would that change the?
No, because you would always have beta 0. In fact, there should be a step 0 where y equals beta 0. But you could just have plus beta 0, plus beta 0, plus beta 0 at the end of all of these. Yeah, and then you would have an intercept.
So I was saying not just have beta 0 in all of these, but combinations where there's beta 0 involved and where there's not.
You could do that. Then that would effectively be, instead of having like 3 variables, you would have 4 variables. So you go up k by 1, basically.
But if we do it for each of them, so let's say in step 2, beta 2x to beta 1x1, we do 1 without the intercept, with the intercept. Same with beta 2x to beta 3x3. So we're adding 1 each.
Okay, you would double it.
Yeah.
But okay, 2k x prime is still way smaller than 2 to the k, yeah.
But the right way to do it would be to have a step 0 where we select the beta norm first.
Yeah, that's right.
And then it goes into the forward norms.
Yes. Yeah.
So, go from step 1 to step 2, you just ignored the combination of the 2 lowest R squares.
Yeah, you just take the highest R squared one and then you move to the next one. And then in your step 2, all of your models have to include this.
Right.
And then in your
and then the remaining variables. and
Yes.
their coefficients.
And then in step 3, your models all have to include this, and so on and so forth. So yeah.
So yeah, it can lead to you not picking the best model.
Yeah, so it is possible that happens. We are kind of doing, you can kind of see the strategy here though, that we say, well, if it turns out like that this thing was important to the model, then it should stand that like it should continue being important. But if there are terms that may, influence that things in combination, then you could miss that, right? Because what are we missing here? We don't have y equals beta 1 x1 plus beta 3 x3. We never tested that here. And it could just so happen that that one is the one that you missed and happened to be the best model. Like, it's possible, right? On the other hand, like this is the trade-off that you are making, is that you can run through many combinations that you wouldn't otherwise be able to, yeah.
Then what was the point of the process of elimination in step 1? If we picked beta 2x2 and sort of said that we will not pick beta 1x1, beta 3x3 in step 2, and if including those could have been the best model, then isn't the approach flawed from the start?
This is the reason, right? Like you are so the idea is that if I think that this is an important variable, I'm going to carry it forward. And it's every step you're like, I'm going to keep the most important variable, okay? And yes, it is possible that you miss things, but the trade-off is that you
We'll
don't.
have to do a lot more computation.
Yeah, exactly.
Especially when we're talking about like 50, 100.
You
300
simply
variables.
cannot test all of that, right? It's not possible. And in fact, once you're at like 9 or 10 variables, it is impossible to do all the combinations. Like, it's literally impossible, right? So this is a very, very powerful tool because you will be working with data sets that have 8, 9, 10, not to mention 50, 100,000 variables. And doing strategies like this are the only way that you're going to even be able to approach like looking at combinations of variables. Okay? Okay. So I mentioned that other people teach this in slightly different ways. So the criteria that we use for moving between steps is actually, we're just doing the R squared between all of these. So why do we not look at some of the other criterion when we're like within a step?
I mean, you're not looking at adjustment because you're using the same number of variables
Exactly.
in each model.
Exactly. And so we wait till the end in order to do that. And on the last step, to pick the final one out of the best in each step, you are then employing those criterion that we're thinking about. Now you're factoring into account like the number of parameters.
With AIC and BIC, wouldn't they be only useful when y is a probability between 0 and 1?
Commonly, that's when you would use it, but doesn't have to be. You can, in theory, calculate likelihoods for like linear models. Yeah. Okay. My word of caution, I mentioned sometimes it's taught, this type of stepwise procedure is taught where they actually do the selection here based off of your standard errors and how significant a variable is. That is like well known to be a terrible way to do this. So yeah, if someone is telling you to do selection based off of significance of your variables, run, because that is the ability of a model to predict good outcomes is not directly related to the statistical significance of your explanatory variable, or it's not sort of directly related. And processing out variables in that way can actually lead to larger issues with the model selection process than this procedure that we're showing. Yeah.
So in the final step, when you run the AIC and BIC, you consider all three of those lemmas, FAIC
Yep.
notation.
Yep.
In using standard errors to pick this, do you mean they recommend using statistical significance to pick which one to take to the next step?
Yeah.
But wouldn't that be flawed? Because then if you take, let's say, beta 2x to the next step and add beta 3x3,
Yeah.
suddenly the significance of beta 2
Yeah.
vanishes.
There's all sorts of reasons why it's a bad way to do that, right? Because yeah, you could have correlations between your variables. There could be multicollinearity. There could be issues related to the error term and your explanatory variable. It's bad. Don't do that. And if someone's teaching you that, take another class. Okay. There's also a procedure known as backwards stepwise regression, which is the exact same as the forward, except you are starting with this and moving backwards. So this is your step one, and then you, instead of adding a variable, you take one variable out at a time until you get down to one variable. And that is also a common procedure. And actually, oftentimes, people will do both a forward and a backward stepwise regression and kind of meet in the middle. Okay. I don't think we have enough time to go through the code for this, so instead I think what we'll do is we'll just start with that next time. So we'll end a little bit early today. And on Monday, we'll pick up where we left off. I'll do a quick review of this, and then we'll just dive right into coding this. We'll do similar to the cross-validation. I'm going to walk through the manual coding procedure to do this. And then I'll show the built-in functions to do stepwise regression. And it will be important to pay attention there because the example for forward, I'm going to go through the example of forward regression manually, and then on the homework, you guys will have to figure out how to do the coding for backwards regression, backwards stepwise regression. Okay. Any questions about any of this stuff? Yeah.
Can this be applied to nonlinear models?
Huh?
Can this be applied to nonlinear models too?
Yes. Yes, it can. We'll see examples of that actually. Yeah. Okay, great.